Welcome, Rob. I'm super excited about this talk. He's going to be talking about consensus and Substrate. Give him a warm round of applause.
Thanks, everyone. Really great turnout. It's super awesome to see all the familiar and unfamiliar faces in the crowd. So yeah, today I'm talking about consensus. I think most of Sub0 is going to be focused on the runtime stuff. So when you're building a blockchain with Substrate, you usually have some idea for a unique state transition, some way that transactions are going to be processed. And you'll do that by writing a runtime. So all the workshops and more or less are going to be about that. The consensus is something that lives outside of the runtime. And I think if you're writing something relatively runtime oriented, you don't need to worry about consensus really at all. There's going to be a couple of calls to instantiate a consensus engine or a consensus engine overseer. But other than that, you don't have to worry about it at all. However, it's still good to be aware of it. And I'll talk about the pluggable consensus system of Substrate, how that works, how we plan to fit that into sort of our overall vision for Polkadot. So without further ado, I would go into a really brief background of the abstraction that we try to make with Substrate. So we split up the idea of the blockchain into a consensus engine, which provides finality on some blocks that do some arbitrary thing, or a fork choice if there's no finality. Finality can also be probabilistic, just informed by some fork choice. And there's some kind of incentives drawn from the runtime, for instance, the staking module from SRML or something else you might write up yourself. Then we also have the state machine, which is the runtime, basically, what's happening when you execute a block or an extrinsic. The actual logic that happens there, the consensus engine doesn't really care about at all. What the consensus engines do, the way that we model this, is essentially consensus engines are watching for signals from block headers. So that means that light clients can follow it as well. So the way that we do signals is with digest items. So there's a special field in the header where you can put any kind of digest. And there's certain digests that are just called consensus. And you can send a message to the current consensus engine that says, hey, I'm changing validator sets, or later on we'll see how we use this to change consensus engines mid-flight. So the diagram of what Substrate's architecture looks like is like this. So you can see that the consensus lives completely outside of the WebAssembly. It's not something that we're trying to do in WASM because consensus involves a lot of different parts, including networking most of the time, having an efficient gossip protocol that actually manages to get all the messages, but not too many messages that aren't, irrelevant messages. Encoding this kind of logic in WebAssembly is a bit too much of a task. So it's better to have it outside, but give the runtime the ability to sort of negotiate between consensus engines. Yeah, so you can see that this consensus piece is completely outside of the WASM. Yeah, so the consensus engine that we've been focusing on for most of our time, I mean, as Frederick said, we have a certain goals at parity that we're trying to hit, and Substrate can accommodate many different kinds of consensus engines, but obviously we don't have time to write all of them. So we've been putting our efforts into implementing Grandpa and Babe. So I'll talk really briefly about basically what those are, what kinds of guarantees they provide. So when you're starting a Substrate chain from scratch, what exactly kinds of guarantees you're getting from those consensus engines that are sort of for now, the blessed ones. So Grandpa is a finality gadget. So Grandpa is meant to be associated with some kind of block production system. So Grandpa doesn't produce any blocks itself. It's meant to be used in conjunction with something that is making blocks. And it does that without bounding that system too much. So that system doesn't have to follow many constraints other than its fork choice rule needs to follow the most recently finalized block, or there's another variant of that, but it's not the one that we're using for now. So anything like that is compatible with Grandpa. So what Grandpa's doing is it's a tweak of, well, it's more than a tweak, but it's building on top of PBFT. So PBFT's working is that it it does 2 rounds of voting, and the goal of this 2 rounds of voting is to get a 2/3 supermajority sign-off on some block hash or some value that's going to be agreed upon. So what Grandpa does is, instead of voting on single values, so Tendermint is also built on top of PBFT, and the way that they've adapted this to blockchain is a proposer puts forward a single block, a single value that they're going to put through 2 rounds of voting and try to garner agreement on. What we do rather with Grandpa is people vote on chains. So they vote on whatever the best blockchain they have is. They just say, okay, this is the hash of the best block that I have right now. I'm going to broadcast that vote around, and let's see what other votes other people are following. So the diagram of what that turns out to be like is like this. So you can see node 1 is voting on, he thinks D1 is the best chain. He hasn't seen those other chains. Node 2 thinks that F1 is the best chain, and node 3 thinks that E2 is the best chain. So these are all nodes that have different views of what the best block is, but the interesting thing is that they all have this common ancestor C. So the goal behind Grandpa is to figure out what that common ancestor is and deterministically finalize it in a way that if that block were to be reverted, we could figure out who had misbehaved, which would require over 1/3 of misbehavior, and slash those people and provide a property that we would call accountable safety. Essentially that the consensus engine is safe as long as less than 1/3 of participants are misbehaving, but if they do misbehave, we can also figure out who that is and slash them, and that provides economic finality for the chain. This is actually the same property that Bitcoin tries to provide with proof of work, or Ethereum as well, the common ancestor property. Basically, the way that proof of work frames it is, if every node just chops off the last n blocks from their chain, they'll all have the same chain. So we're doing that, but in a deterministic way. And because we don't have to wait for n blocks, we can do it much faster. So that means that in periods of good network communication, you can finalize stuff very, very quickly. Whereas when there are not periods of good network connection, you're not finalizing anything new. But as soon as the network connectivity is reestablished, you would finalize a bunch of stuff. So we couple that with BABE, which stands for Blind Assignment for Blockchain Selection. So that is heavily inspired by Ouroboros Praus. So Ouroboros Praus is it's a block production mechanism, which basically it splits time up into slots. So we sort of did one of the earliest versions of this family of block extension algorithms. We call it Aura. So the idea behind this family of block production algorithms is sort of like proof of work. You're not doing 2 rounds of voting before adding a block. You're just splitting up time into discrete segments and adding a block. Like, there is a leader for each of those slots. We split up time into slots, and there's a leader for each of those slots, and that leader authors something. So Aura is the simplest way to do this. Aura is split up the time into slots, and every slot has a leader, which is chosen by a round robin. We just go in a circle. That has some issues which are solved by Ouroboros Praus. So what Ouroboros Praus instead is doing is everybody has a random key, or like their own private key that can be used to produce deterministic signatures called VRFs. And basically, you don't know that somebody else is the slot leader until they prove it to you. And that means that as an adversary, you can't predict who's going to be authoring the next blocks, and that makes it a little bit harder to attack. But what we do with BABE is we take that one step further. There's a couple problems. I think the one in chief that we try to solve with the initial implementation of BABE is the problem of clock drift. So the idea is, if you're splitting up time into discrete slots, so I say every 4 seconds, so the first 4 seconds, that's slot 1, the next 4 seconds, that's slot 2, the third 4 seconds, that's slot 3. The problem is this is a decentralized network, and people can have different views of the time. So my view of it's slot 1 right now may not overlap with all the other authorities' views of it's slot 1 right now. And that can lead to some kinds of attacks. So some people did a paper where they analyzed this family of consensus algorithms, and they found that clock drift can be used to perform attacks a bit more cheaply than you might expect if you don't account for this problem. So you can see here that there's 2 partitions of nodes, A1 at A2, and they're seeing slots at slightly different times. And these gray bars are where the adversary can get up to some misbehavior. So what we do with Babe is basically we use an approach that we call relative time, which is essentially you watch, you know how long the slots are supposed to be, but you don't know when they start or end at the beginning. But then you watch at what time you are importing new blocks. So you import a block that says, I'm at slot 100. You're like, okay, great, I'll make a note of that. And then you get another block that says, I'm at slot 101, and another one that says, I'm at slot 103. And once you get all these new incoming pieces of information, you can start to figure out where the rest of the network, accounting for adversarial behavior, thinks the slots are. And you can make an estimate that slightly overestimates the time of each next slot. So that means that clock drift as an issue is eliminated. So this is the main change that Babe is making over Ouroboros browse, and that should make it a bit more resilient to MTP server attacks or geographic distribution of nodes as well. Yeah, so basically that's Grandpa and Babe. That's what we try to set out with Grandpa and Babe. When you just run a substrate node, that's what you're going to be getting. Although for now with 1.0, we're running Aura, and you can opt into Grandpa, but the APIs are not necessarily stable so far. So they're not likely to change. The high-level APIs are not likely to change too much, but they will be changing for now. Aura is the only stable consensus engine in 1.0. So now I talk about, for those of you who would write their own consensus engines, or at least want to know how the consensus system works in Substrate, the building blocks of the code. So there's a few key abstractions that we take for pluggable consensus. The main thing is that we want to isolate as many of these components from each other as possible. So every consensus engine can specify its own import queue. So this might do parallel verification. The key thing is it does verification in a manner where it doesn't matter if the blocks are out of order. So you could do block 3 before block 2, or block 5, then block 7, and then block 1, right? So some kind of first stage verification, which is usually something like checking that the block has actually been signed by the person who is supposed to produce it. We're checking that that's a valid signature and whoever signed it is indeed an authority. It doesn't do block execution yet, because block execution has to be in order. So that's the next piece. We have a block import worker. So most consensus engines don't have to care too much about this because the client struct is, the client wraps a database and it handles most of import. That's all actually an implementation of this trait. So most of the time you can just use client for this, but for Grandpa, for instance, you have to do a bit of extra work for every block, and you have to track certain properties of all the blocks that are coming in, and you need to do this in order. So that's the kind of situation where you write your own block import struct that wraps a client internally, but on either side of that call does its own logic and does its own bookkeeping. And the most important thing that we try to isolate is the background workers. So basically, all the pieces that are doing things like interacting with the network or authoring blocks or casting votes are their own asynchronous tasks. So those don't get told what to do by anything else. If you would try to set up a pluggable consensus architecture where the engine is called at specific places, like, oh, now is the time to author the block, you can't make that abstraction actually stretch to cover enough consensus engines. Whereas the abstraction of just having something that works in the background and has access to the network actually works. So you can use basically these 3 pieces to write basically any consensus engine we can conceive of. Like, I haven't run into one that wouldn't fit in this architecture. So if you're interested in working on a consensus engine, the consensus directory of the code is the place to go. And it has definitions for all these abstractions in a bit more depth. So a bit of a diagram just to show exactly how these pieces are fitting together. We have the background worker and the import queue talking to networking. The import queue is getting blocks from networking. The background worker might be receiving messages or sending messages. It doesn't have to. I mean, for instance, for proof of work, you don't have to do any kind of special networking. Same with Aura. You just have that block import pipeline and the ability to broadcast blocks. And For more complicated engines like Grandpa or Tendermint, you're obviously going to the network all the time and casting votes and gossiping stuff around. And both of these things talk to the block import workers. So the main thing to note is that the block import thing doesn't really care whether the block was authored by us locally or coming from the network. The logic will be the same. And that's how you ensure that you have consistent behavior and you don't accidentally do one thing for blocks that are coming from the network and one thing for blocks that are coming from your local node. So the next section of the talk, I would talk about Cumulus. So Cumulus is a project that we're doing essentially designed to bridge the gap between Substrate and Polkadot. So the idea is many of you, I would imagine, are here to learn how to write parachains, or at least interested in writing a parachain. If you're not, then you can ignore this. But if you are, Cumulus will be very interesting to you. The idea is we have to write a blockchain in Substrate, but turning that into a parachain is actually not that easy. So Cumulus is a set of libraries designed to bridge the gap. So it's a set of libraries providing a Polkadot consensus engine. So it's just a consensus engine that's built with these previous primitives that knows how to follow a relay chain and turn a Substrate runtime into a Polkadot validation function. And that's split up into a couple different parts. So, one part of that is authorship, and the other part of that is finality. And you get finality just by following the relay chain and seeing when that's finalized. And you get block authorship by running a Collator node. So this is intended to be used to turn any already written Substrate codebase into a parachain with minimal code changes. Ideally 0. I think for now we're looking more like minimal code changes, but I think further down the roadmap it's going to be more like just do a signal in your chain and it can automatically activate Cumulus. So the key thing that Cumulus is doing is it's actually, and it's a bit of a weird wrapper, but you have a blockchain node that's internally running another blockchain node, and that other blockchain node is a Polkadot Lite client. So your consensus engine is actually wrapping another blockchain node, which has its own consensus engine. So that'd be a little weird if you diagrammed it out, but that's actually the only way to do it. So from just a really quick overview of Polkadot, we've got the relay chain, which is it has its own finality, it's got its own consensus, and the idea here is to provide security to all the different parachains and pass messages between them and provide security on that operation as well. We have the parachains, which are some unique state transitions that each do their own thing, have their own blocks, have their own authors, and have their own specialized purpose, but they know how to talk to each other so that you can build apps that leverage all of them. And then you have bridges, which are linking to blockchains with their own consensus. For example, bridging to the Ethereum network, or bridging to Bitcoin, or bridging to Zcash. These already established networks, which obviously you're not going to just rip up and port onto Polkadot as is, because they have their own established communities. It makes more sense just to bridge them. So with Cumulus, we're really caring more about just parachains, not bridges. So bridges have to be written in sort of a specialized way that accounts for consensus of that other chain. Cumulus is more for native or sovereign parachains, where you have a chain that's designed not to have its own security, but just to attach to the Polkadot relay chain. So what goes into a parachain is the validation function. So the validation function is it's a piece of code registered on the relay chain, and the goal is for collators who are making blocks to find an input to this validation function that makes it evaluate to true. And validators are supposed to vote for things that make the validation function evaluate to true. So validators aren't figuring out what those block inputs are that make the validation function say, okay, but they are validating them, and that is their only job. So validation functions are all deterministic and self-contained. It's a blockchain, you can't have stochastic, random processes, you need everybody to be in consensus with each other. So the signature of a validation function is this, basically. It's the last header of the chain, it's the information about the relay chain at that block height, and it's the block data. So the block data is essentially they're just bytes, and the function implementation will tell you if those bytes are a valid block or if they're not a valid block. And the output is maybe a new header, if that's okay. So to talk about exactly what that block data is, we need a little bit more context. So to talk a bit more in depth about collator nodes have the job to compute block data for a parachain to make that validation function return successfully. So that depends completely on the parachain. I mean, for instance, if you would have a smart contract chain, the block data would be a bunch of transactions, maybe a header that has a gas limit in it, and it would be also all the necessary state data to execute those transactions, those sorts of things. For a UTXO chain, it would be all the new UTXOs and also some kind of Merkle proof of a database that had been committed to previously that told you what the pending UTXO set was. So collators have to have this specific logic that knows about the chain that it's collating for. So we wrote Cumulus collator. So Cumulus collator is a block authorship pipeline for Substrate. It fits under this consensus engine framework. It's just going to be a background worker, essentially, that creates a block and sends it around with the state tree proofs of all the data you need. So for instance, if you are accessing some storage in that block, whoever's validating that block needs to also have access to the storage, which means you have to pass it into the validation function. So what Cumulus collator is doing is just ripping out a subset of the state tree that is needed to execute all those transactions and sending that along with the transactions, as well as any incoming messages and all the state data needed to execute those incoming messages. So what the Cumulus collation pipeline looks like is essentially this. You have incoming messages and other relay chain data. So that might be, for instance, the previous relay chain header hash, or some data about which other parachains are registered, or I guess trust wormholes or something like that. And then on the other side, you're doing the parachain stuff, which is selecting a set of transactions from a queue. And then you sort of combine these two pieces of data together, you do a proof of executing all of that, and then you send that out into a POV block or proof of validation block. So the main other way that parachains differ from sovereign chain substrate is that they have to follow the relay chain. And I won't spend too much time on this, but basically we know that the relay chain is going to be finalized with grandpa consensus. So parachains are getting finalized via the same process. You have some parachain hash that's committed to in some relay chain block, and if that relay chain block is finalized, then with good assurance we can say that parachain block is also finalized. That means that we can always find the latest finalized header for a given parachain. That's easy. And if we were just writing a light client, that would be fine. But for full nodes, we have to download all the blocks of the parachain, from the genesis to the head of the chain. So, we know what the genesis is, obviously, and the head of the chain we can figure out from the relay chain state. But what's in the middle, there's basically two approaches. So one approach is download that all backwards and then import all of them, because it's a linked list. You can easily go from the latest finalized block to that parent and that parent and that parent and get the whole thing backwards. But that's a lot of space that you would be kind of doing nothing with, and you have to wait a long time before actually executing anything. So the other option is download forwards. But if you're downloading forwards, you have to figure out whether, okay, I know block 1 million is finalized, but I've got block 1000. How do I know that this is actually on the same chain as that block 1 million? So finding the canonical hash of an older header isn't that easy, but the way to work around it that we do in Cumulus is to use log2 ancestors. So basically, the parachain state is keeping a bunch of header hashes, and these header hashes are the hash of the most recent ancestor in its history, whose number is a power of 2. So, the text description is a bit hard to understand without a bit of a diagram. So the diagram is here, for instance. So it's like we have a bunch of tables, or a bunch of rows in a table, and each row corresponds to some power of 2. So we have 2 to the 1, 2 to the 2, 2 to the 4, 2 to the 16, 2 to the 18. We'll have them probably up to 24 or 32 or something like that. And then when you import a block, you can easily update all the relevant rows in the table. You'll squash some number of the rows. Like for instance, if I were importing a block where its number was divisible by 2 to the 4, I could squash the rows for 1, 2, 3, and 4. Because those are sort of supersets of each other. What this lets you do is, from a finalized block, sort of take bigger hops backwards. And that means that you can use this in parallel with synchronization forwards and find basically what block hash is canonical at some number. It's not an instant process, but it's a quick process. And that means you can do checks periodically and immediately, or fairly quickly discard chains that actually aren't the one that you're looking for. And that's basically what this diagram says. So just to tie it all together, Cumulus gives you a consensus and chain synchronization implementation for Substrate. It follows a relay chain, a Collator node for producing blocks, and tools for writing Substrate runtimes that send and receive messages to and from other parachains. And this is basically more or less all written by us, except for, of course, the runtime component, which you have to write your own logic for dealing with incoming messages and for sending outgoing messages. Other than that, this is all just encapsulated within the Cumulus consensus engine. So to get started with Cumulus, it's definitely in the very early stages of development. So we've got the draft of the collator in. The repository is parity_text/Cumulus if you want to take a look. But basically, to get started with Cumulus, if your plan is to use something like Cumulus, the best step forward is just to start writing your chain with vanilla Substrate, with the expectation that it's going to take very minimal changes to port it onto Cumulus now. So you don't have to worry about when is Cumulus going to be ready, because you don't have to worry about that. You'll just write your chain with Substrate 1.0 or with 2.0 as we release that further down the line, and then as soon as Cumulus is available, you can just plug right into that. And that sort of leads into the next question, which is, okay, but what if I want to deploy my chain before Cumulus is ready? So, and then later turn it into a parachain. So that basically leads into swappable consensus, which is the feature of swapping consensus engines in mid-flight. So you start the chain with one consensus engine and you immediately switch to another. The way that we would do this, well, let's revisit this. So we have these few sort of abstractions: background worker, block import worker, import queue, and those communicate with networking, and the networking interface that they have is very general. So what we can do is basically write each of these components to be a wrapper around several consensus engines. So we can write some kind of overseer background worker, some kind of overseer block import, an overseer import queue, where it knows what consensus engine is currently in use, starting from the genesis and following some kinds of signals that are coming out of the chain, and it'll dispatch blocks to be verified to the correct piece of logic, or it'll poll the correct asynchronous background worker to completion. So for instance, if you have grandpa consensus activated, the overseer will be aware of that, and it will poll the grandpa finality voter. So the way that we do this is we categorize consensus engines into two categories. So we have finality providers and blockchain extenders. And you can only have one of each registered at any given time. Some consensus engines may fulfill both. If you have an instant finality, PBFT-based kind of consensus engine, that's clearly extending blockchain and also providing instant finality. So that's both. It doesn't make sense to have another thing providing finality as well. And it doesn't make sense to have something else growing the chain if the thing that's coming out of the instant finality engine is going to be instantly finalized anyway. So we have the consensus overseer, and this is hinging on basically a consensus engine ID type. So for all the consensus engines that we're going to bundle with Substrate, and there's going to be a number of reserved IDs for this, they'll just be automatically included in the overseer. But of course, you can write your own and register them also into the overseer. So that means for a typical Substrate chain, you'll just have some call in your CLI file or your startup file that says, start the consensus overseer. And that's all the worrying you have to do about consensus, because it's handling all the negotiation between consensus engines and everything internally. So you don't have to worry about, which consensus engine am I going to run? The chain's genesis will just sort of tell the consensus overseer that, and it'll know where to pick up. Yeah. So the way that we switch consensus engines is basically by issuing a signal in the header. This is the classic modus operandi that we're using to, cause consensus changes. And the reason we do it in the header is mostly so that light clients can follow along as well. So we have this consensus digest. You can issue this in the header, and it'll have a consensus engine ID. And if that consensus engine ID is equal to the overseer ID, the message body, if it's valid, would probably contain a signal saying, hey, I want to change to this new consensus engine. So when do we do the consensus switches? So for finalization, we change it when the change block is finalized. So that's the block that contains the signal. Whenever that's finalized, we will change the finality gadget. And with chain extension, we'll actually start building on that immediately. And chain extension is the trickier case. So with chain extension, of course, you can have forks. So if you're dealing with two unfinalized forks, which both signal a consensus engine change, it's relatively easy to deal with finality. Because finality, it'll just wait until everybody sort of has the same view of things. With chain extension, you can all of a sudden have two competing chains, and the fork choice rules are a little bit hard to reason about. For instance, you have two chains, and under a chain extension A consensus, one of those chains is better than the other. Chain A is better than chain B. But then you switch over to fork choice rule from the next consensus engine, and all of a sudden they've sort of flip-flopped. So the question of which chain to build on is not that easy. But generally, the solution is going to revolve around having a standard sort of set of rules for migrating fork choice rules from one engine to the other. So, for instance, if both chains have a longest chain rule, this is relatively easy to do. If you're migrating from total difficulty to longest chain, then you need some kind of adapter in the meantime. But those can not too difficultly be written. Yeah. So that's all I'll talk about for now. Of course, if you have any other questions, you can come up to me after, or if we have a bit of time left for questions, just ask them now. Thank you very much.
We should have some time for questions if there are any. I can run the mic around. If no one has questions on this, you are so much smarter than I am. All right, I guess you're super smart.
I lost my voice a bit, so excuse me for that. I would like to ask about your mindset, security mindset when you are building consensus algorithm. What are you expecting from the network? Are you preparing for the nodes hijacking, malicious actors? Like, up to what security guarantees you are going to operate?
Yeah, that's a good question. So basically, when writing a blockchain node, you have to deal with peers kind of sending you any kind of shit, right? And we've incorporated basically a piece of architecture into our consensus engine's design. So specifically that networking portion is driven by, essentially we're doing a constant cost benefit analysis of all our peers. So for instance, if a peer sends us a packet full of junk data, then this is a cost, right, with no clear benefit. And we're going to prune peers that provide high cost with no clear benefit. Whereas if a peer is feeding us new consensus messages, this is a high benefit with relatively little cost, and we're going to keep those peers. So this is sort of a natural economic mechanism for filtering out bad peer sets, and you can encompass basically any kind of misbehavior with that. Then the question is, the other kinds of misbehavior are a bit trickier and you can't quite solve them at that level. For instance, things like double signing or collusion-based attacks, and this is where we have the higher level protocols like equivocation or double voting detection, which is generally the easier of the two to do, and then we have accountable safety protocols. And for Grandpa, we have this. For Babe, there's nothing you can really do except for the equivocation stuff. There's no kind of collusion protocol that you can run against a Babe attacker. But yeah, these are generally the three levels at which we're trying to protect against attacks, and that encompasses more or less all kinds of misbehavior.
Excuse me. I have a question. So, with Grandpa consensus, so you said the next block producer is chosen by round robin, right?
That was Aura.
Yeah. So, does that mean that the number of block producers in the network are deterministic, or is it decided upfront, or how does it work? How can a block producer join the network?
Yeah, that's right. So I think this is, these are all, I suppose, the terminology that people tend to use is permissionless versus permissioned, but this is not really the best way to frame it. It's more that all of these consensus engines, which I've mentioned, so Aura, Ouroboros, Grandpa, Tendermint, all rely on a set of validators having been registered on-chain. How that process is actually done is ambiguous from the perspective of the consensus engine. With Aura, you do have to be registered as a validator, right? So, whether you've done that by some staking protocol or if you've just been, given authority by the creator of the chain, who knows? But the main problem with Aura is that you don't scale that well to very large numbers of validators because you're going completely round robin, which means that if you have a turn now, you're not going to have a turn for a very long time later, and everybody can see exactly how long it is until your next turn is. Yeah.
All right, we are going to have to cut to the next talk. So we're switching modes a little bit, but thank you, Rob, very much, and give him another round of applause.